Now we'll take a look at how the sorting algorithms that we talked about are expressed in the systems that we use every day. Now the key point is that sorting algorithms are essential in a very broad variety of applications. All of us use sorting algorithms pretty much every day. Many obvious applications like organizing your music library or displaying your search results or listing feeds in your web browsers. There's some other applications that are not so obvious where we use sorting as to make a problem easy once you know that they're sorted. And so, for example, finding the median. If it's already sorted, then it's easy to find the median. And other statistical problems are like that, or finding duplicates. The problem of finding duplicates by itself is not quite obvious what to do, but one easy way to solve it is to just go ahead and sort. And then there are plenty of applications that we'll see later in this course, like data compression or computer graphics, like finding the convex hull, applications in science, such as computational biology, or in systems development, where having an efficient sort is absolutely crucial. So because there's all these applications, most programming systems have a fast sort as an important part of their infrastructure. And Java is no exception. So Java has a method called arrays.sort, and it's intended to be a general purpose sorting method for use by Java programmers. And now that you have some understanding of the classic methods, you can have a better idea of why arrays.sort is the way that it is. It has the infrastructure that allows it to be used for all types of data types and all types of ordering. So it's got a method that implements comparable, and then it's got a method that uses comparator, so that you can use the natural order, or you can provide a comparator and provide your own order for any type of data. It uses actually both quicksort and merge sort. It uses a tuned quicksort for primitive types of data and a tuned merge sort for objects. Why two different? It's just the designer's assessment of the idea that if a programmer is using objects, maybe space is not a critically important consideration. And so the extra space used by merge sort maybe is not a problem. And if the program is using primitive types, maybe performance is the most important thing, and so they'll use the quicksort. To invoke arrays.sort, you have to import the namespace from Java util arrays, and then all you need to do is invoke arrays.sort. I just answered this question, why do we use different algorithms for the two types? And this is maybe arguable. Now, I referred to this idea of a good system sort. There was a good system sort that a lot of people used for many years. And in 1991, there were some scientists at Bell Labs that were using QSort for a scientific problem, and they were used to it taking just a few minutes, and then they realized that it was taking hours of CPU time. And the fact was that all the QSort implementations at that time in Unix had this flaw. Well, there were two flaws, and one of them's a little complicated about the way the array is ordered. The other one was for arrays that had lots of equal keys, and this Wilson-Becker problem had lots of equal keys. It was quadratic time. System designers, John Bentley was one of the designers who took a look at this problem, and that led ultimately to the development of the three-way quicksort that we use today. He worked with Doug McElroy, and they wrote a paper that outlined this problem and talked about some of these things. And they had a three-way partitioning method that was somewhat like the Dijkstra method that we showed, but a bit more complicated. Another thing they did was, rather than shuffling the array, they used what's called a method for choosing a partitioning element called Tukey's ninether. Tukey's a statistician, and he had this particular method for order statistics that has some interesting properties, and used that for the partitioning element. This paper was very influential, and that basic method is widely used. And Tukey's ninether is just pick 9 items out of the array and take the median of the medians, and that's the ninether. Very inexpensive, and they had macros to do this, so it used not too much cost to find a partitioning element that's much closer to the middle than if you used a random one. The reason they used it is they thought it got them closer to the middle, and they also don't like some system designers don't like the idea of using random choices in a system method because of the way that it changes the state of the system. So they felt that it got better partitioning than a random shuffle, and it was also less costly than generating random numbers, including this change of state problem. But there's a problem. So you would think that the system sort would be completely solid with all this research and all the development that's gone into it. And in fact, there's a file out there, and you can go to our book site and get it, that will actually break the Java system sort. There's a killer input that will make the thing run in quadratic time. Actually, it usually crashes because it's recursive and it crashes the system stack. And it can cause all sorts of problems. There's a killer input for the system sort. And it can be disastrous in various systems. And the reason is they didn't do the random shuffling. McElroy himself actually found this problem that you could, while the sort is running, figure out an input that would make it crash. And so you can just run that program. If the sort doesn't use randomness, then it's vulnerable to this attack. So which algorithm should we use to sort? That's really a key question. We've looked at a lot of sorting algorithms, and actually there's hundreds of sorting algorithms out there. We've chosen the most important and the most interesting for you, but you could literally spend a year reading all the papers on sorting. And they still continue to be invented. New algorithms are developed that are found to have good characteristics all the time. And really the key idea is really important to think about because it applies to all sorts of algorithmic problems. On our way, we've been talking about rules of the game. What is it that we care about in a sort? It's a little bit more complicated than just put stuff in order. There's a lot of attributes that different applications have. Like stability, that's a fairly sophisticated attribute that you really have to think about and maybe not be aware of. Maybe your computer is parallel. The sort has to be parallel. We found that equal keys make a huge difference. And I didn't really think about that at the beginning, but it can make a huge difference. Maybe the way your computer's memory is organized make a difference. Maybe the keys are small and the items are large, or maybe the keys are really huge. Do we need guaranteed performance? Are we happy with random performance? Do we know, is the array randomly ordered? You can think of a matrix shown on the right here where we list out all the possible attributes, and then there's algorithms that work well for different combinations of attributes. But the thing is, there's way more possible combinations of attributes than there are algorithms. So there's going to be situations that are going to require an understanding of what it takes to engineer a sort method that's appropriate for your application. There can't be a system sort out there that's going to cover all possible combinations of attributes. Now, usually it's going to be good enough, but it's definitely worthwhile to understand what's going on with different sorting algorithms in order to even find improved performance over the system sort. So here's a summary of some of the things that we've talked about. We've talked about 6 different sorting algorithms, and we've talked about a bunch of attributes. For example, the top line, selection sort is in place. It always takes about n squared over 2 comparisons. And one of the things to remark about it is that it only uses n exchanges. And so forth. Insertion sort, best case linear, quadratic, in place and stable, and it'll work well if the file's small or partially ordered. Shell sort, we don't know. It's running time. It's not stable, but it's a fast method for intermediate size files and not much code. Merge sort, n log n guarantee and stable, but not in place. Need that auxiliary array. Quick sort, not stable. Quadratic time, worst case, but that's unlikely to occur if you do the random shuffling. And it's the fastest and most useful in practice, particularly if you make improvements to deal with duplicate keys. And it's interesting to note, we've looked at important and classic algorithms that are widely deployed, but we don't have a useful practical algorithms in wide use that's got all of these characteristics. That's in place and stable, worst case n log n. There's versions of merge sort that come close, but they're too complex for practitioners to have adopted them. Those are some of the situations that we encounter when developing a system sort, and quicksort certainly plays a role in most system sorts.